Yeah. So I am Harish Krishnani. I am a PhD student at ISER Mohali, and I will be conducting your, mm, uh, you can say, tutorials for this course on each Friday from 6 to 7. So we have already seen assignment 1 and assignment 2 of the last year, the graded assignments, and we have discussed the solutions of it. So today we are going to discuss assignment 3 of the course offered in 2021. So let's start with the question number 1. So it says, let the symmetric group S5 act on the set 1, 2, 3, 4, 5. That's the indexing set from 1 to 5. Naturally, this gives an action on the power set Px. What is the size of the stabilizer of the subset 1, comma 2 uh, belonging to this power set of X? So I hope you guys are following the lectures. So it's already been explained uh, what is the uh, natural action that we get to a power set of X if G is already acting to the group. G is already acting to the set X. So, but let me revise that part. So I hope you guys can understand how S5 acts on this set 1, 2, 3, 4, 5. So S5 is just the permutations in 5 symbols. So any element of S5 will permute this subset 1, 2, 3, 4, 5 accordingly. For example, say this 1 comma 2 belongs to S5. So, uh, not S2, it is S5. So 1 comma 2 dot 1 will be 2 because it's mapping 1 to 2, and 1 comma 2 dot 2 will be 1 because it's mapping 2 to 1. And for all other elements, it will just fix that element. Okay, so that's the action of uh, Sn on a set on n symbols. Now, this induces action on the power set of this X. So this is our X. This set is X. So S also acts on P of X in the following manner. See, for this group action, first of all, it's like a map from S cross Px to Px, right? So for each tuple sigma, here we are having our S to be just S5. So for each sigma in S5, and for each subset A of power set of X, you should map it to sigma dot A. Now, what is this sigma dot A? The natural uh, action we are talking about. So A is a subset of X, right? So, and sigma is acting on X. So sigma of A will again be a subset of X. Uh, that means sigma dot A belongs to power set of X. First of all, this condition we have to see. So sigma of A is nothing but sigma dot A such that A belongs to A. See here we have seen this action of S5 over X. So for each element of S5 and each element of X, you can see what is sigma dot A, right? So that's what we are doing here. If you are taking a subset A, then sigma dot A is the set containing all elements of the form sigma dot small a, where a is inside a. Okay. Now this dot, or just for the sake of notation, uh, let's say this section was, this action was say action 1. So, and this action was action 2. So this sigma dot a is defined for action 2, and this is naturally coming out from action 1, right? Because a is an element of a, capital A, and capital A is a subset of x. So sigma dot a makes sense, right? It's just you have already seen this action above, right? So that's what the definition of these actions. This is already been described in the lectures as well. So now we have to see what is the size of stabilizer of 1 comma 2, the set 1 comma 2. Okay, under this action 2. So stabilizer, I hope you know its definition, but for those who are not able to recognize it, let me just state it once again. So stabilizer of this set 1 comma 2, we go through the definition of the stabilizer. It will be the all sigma belongs to G, that is S5, such that it fixes this subset. Okay, sigma dot 1 comma 2 is again 1 comma 2. So it stabilizes this subset. After this its action, this set is again mapped to this set. It's not being mapped to somewhere else. So we need to find all elements of S5 such that sigma of and what does this means? This set is nothing but the set sigma of 1 and sigma of 2. Okay, so we need to find all those elements which uh, fixes this subset 1 comma 2, and we uh, we can do anything with the other three elements, right? So there will be two types of such permutations. One is if sigma belongs to, or let me state it in a more formal and easier way. So see, this sigma belongs to S2. Do you guys agree? Uh, because what we can do, we can just permute these two elements, the element 1 and element 2, and we can't map it to somewhere else. So this sigma is an can be realized as an element of S2, a permutation in two variable, right?
Yes, sir.
If or if it mm, okay, or I should say more explicitly, a sigma restricted to 1 comma 2. This subset is an element of S2. Now I think it makes more sense, right? When it's restricted to one this set, it has to permute this set only. It can't be mapped to something somewhere else. And what about others? That sigma restricted to 3, 4, 5. Now see, for these elements also, sigma can't map any of these to 1 or 2, because 1 and 2 have already been mapped to 1, 2, right? So 3, 4, 5 again has to be mapped to 3, 4, 5. So this belongs to S3, where this indexing set is 3, 4, 5. Any permutation restricted to this 3, 4, 5 has to permute this 3, 4, 5. Yeah, it's clear. So sigma when restricted to 1 comma 2, it should be an element of S2, and when it's restricted to 3 comma 4 comma 5, it has to be an element of S3. Okay, so what you can say here, how many choices you have, number of elements of S2.
Two.
Yeah, 2. uh, and for this, how many choices you have?
Six.
Yeah, 3 factorial, that is 6. And both of these events are independent, so total choices is, any guesses?
2 plus 6.
2 into 6, that is 12, right? Because for each such choice of sigma, you can get a different permutation in these three, 4, 5, right? So it's just S2 cross S3. The set is just same as the set S2 cross S3. It's a group, you can say it's a group isomorphic to S2 cross S3. If you're a bit confused, then let me give you some examples so that uh, you can understand it well. So see, what we are supposed to do, we need to find sigma in S5 such that when sigma is operated on this 1 comma 2, it fixes 1 comma 2. So if you are having 5 symbols, 1, 2, 3, 4, and 5, and say this is your domain and this is your codomain. So whatever sigma you pick, it has to fix this 1 2 as a set, has to be mapped to this set, and your 3 4 5, this as a set has no other choice because 1 2 has already been mapped to 1 2. So this has no other choice, but it has to be mapped to this 3 4 5. Now for this side, you can do this in 2 factorial ways, and here you can map them in 3 factorial ways, right? So total is 2 factorial cross 3 factorial, that is 2 into 6, which is 12. Okay, so I hope it's clear to everyone. If anyone has any doubt, then you can ask me. If it is okay, then we can move to the next question. Okay, I hope it's clear to everyone. Let's move on to the next question. The next question says, in how many distinguishable ways are there to paint the three edges of an equilateral triangle with two different colors, assuming that the same color may be used in different edges? Okay, so you need to you have an equilateral triangle. So let me first show it equilateral triangle. So say we have two colors. First, this color, and let me choose a dark one so that it's easily distinguishable, and this one. Okay, so these are our two colors. So we need to color an equilateral triangle with these two different colors, assuming that the same color may be used in different ages. So there is no foundation. We can either use the same color to all the edges, or we can use a different color to the edges. So there is no foundation. So in how many ways you can do that? So first of all, this is a choice. You can map all three sides or edges with the same color, right? So this is choice number one. Oh, I'm using the same color. Only this is so. This is choice number one. What about this? It's also a choice because the question says it may you may use different color. It's not an obligation that you have to use. Sorry, you may assuming that the same color may be used in different ages. So you may or may not use the same color. So if you use the same color through for painting your all three ages, then it's okay, uh, right? Now for a change, we paint one side with this light blue color and the other side with this color, and then this side again with this color. So this equilateral triangle is surely different from the first two. And is there any other option remaining? First of all, three is not a choice in the available options, so at least something else should be there. So can any one of you just let me know what is the possible choice or choices?
One side is black and two are the blue.
Yeah, that's also a choice. Good, Shalini. Uh, so the one side is black and the other two is blue. And whatever else you pick would be a rotation of these four. We will see how to formalize this thing using the group action also, but at least you can realize that there are four possible choices. If you color this side and this side blue and this side black, then it will be a rotation of this side. Similarly, if you color some other sides to be black and one side to be blue, then it would be a rotation of this triangle. So it it won't be distinguishable, right? That's why it's written that how many distinguishable ways you are there to paint it. For example, if you do like that, uh, these two to be black and this to be blue, then it's just a rotation of this, right? It's just a rotation of it, so it's not distinguishable. So whatever else you pick has to be one of the rotation of the already mentioned three choices. So there would be four ways to paint the sides of an equilateral triangle. The next question is also of the similar nature with a slightly different condition. And after doing this question
We
manually, I
argue
will just
that
let you know how to
because
write these things in
the
terms
action
of.
has to remain finite
Uh,
at all, because it's an integration over all the
so,
coordinates, and the action has
Malika, can you
to
please
necessarily
mute
remain
yourself?
finite, because otherwise we can't really compare between.
Thank you. So the next question is, in how many distinguishable ways are there to paint the three edges of an equilateral triangle with four different colors, assuming that the different colors are used for different edges? Okay, so in this case, they are saying that you have to use different colors for all three edges. So first of all, let me choose my four colors. First is blue. Second, let's go with the green. Uh, then black. Then this red one. Okay. So see, you have to use different colors for for all the three edges. So of course, just choose any three of them and leave the one,
Yes,
right?
sir.
It's like choosing three from the
Three
four
from
available choices.
four. Yes, sir.
You all agree? You have to
Yes,
choose
sir.
three because without with two colors or one color, you can't color all the edges with different colors. You have to choose three, and you have four uh, in your bank or your bucket. So the number of choices is
4C3.
yes. So number of choices is 4C3. That is just 4 factorial, 3 factorial, 1 factorial, that is 1 factorial, and that is 4. So here also we are getting 4 as the answer. But that whatever we have done is the manual calculation, although we don't need the group action here, but I think it's a good time to just introduce you to a different group action, which is not needed to solve this problem, but it's very much related to whatever we are doing. So uh, let's say the group G is D3, and that's the dihedral group in three dihedral group of order 6. That is the number of possible ways of rotating or reflecting uh, equilateral triangle. Okay, so it's the group of all symmetries of the equilateral triangle. So and X is the set of all possible ways to paint an equilateral triangle. Okay, so can we define an action of this G over this set X? So for that, first of all, we need to define a map from G cross X to X, right? So the tuple G comma small x has to be mapped to an element G dot X of X. So can anyone guess that what is the natural action which is coming out of this? G is the group dihedral group over three letters, and X is the number of ways to paint an equilateral triangle. So what G dot X can be? It has to be an element of X. That means it has to be a way in which you can paint your equilateral triangle. So it's not that much obvious, but still you can get the intuition. And once I write, it should be clear. So G dot X is just, so it is the painting that you can uh, first painting the edges in the manner X, and then uh, use, okay, and then rotating or reflecting the triangle by G. So you first need to paint uh, in the manner X, and then you have to rotate it or reflect it according to G. So it should be clear once I give you some example. So let's say this is the triangle with the vertices A, B, and C. And what this painting X does, it paints the one side with this color blue, the other side with green, and the third one by red. So it's after operating this painting X, and say your G is 1 comma 2. So what this or let me write it in some different color, the green one. So for G in 1 2, what you ask, how this 1 2 acts on this triangle ABC. Oh, oh, so I should use the letters 1 2 and 3, because we are using the indexing side to be the numerical ones, not the alphabetical. So it's just A, B, C, A. Oh, again making the same mistake. 1, 2, 3, 1, 2, 3. So what it will do? So this is your original triangle. It will just switch 1 and 2, right? So it will, after switching, it will be 2, it will be 1, it will be 3. So what is G dot X? So your G dot X over this triangle 1 2 3, what it will do, it will first paint it with X. Okay, the same thing. So advantage of working online, that you can copy and then you can paste. Okay, so this is through the action of X. And what G will do, G will then permute it, just permute the symbol 1 2 and 3. It will just permute the symbol. So at the top of it, it would be 2, and here you will have 1. So this is the coloring. This is what you will get after uh, acting this G dot X over this triangle 1 2 3. Okay, so what you are actually doing in the above question, so we were just computing the orbits of this action in question number 2 and question number 3. Okay, so that's up to you how you realize it, but as I promised you that I will relate all these things to the group action. So that's I'm doing in question 2 and question 3. We somehow computed or let me just write, we somehow uh, used this action. Okay, so it's up to your understanding how you realize this statement. For your help, I can tell you something in question number 2. So but for 3 you have to realize of it of your own. See, we what did we do? uh, this element and this element has the same orbit when you see it as the action given below, because uh, g dot x will send the triangle to this and this. Okay, that you have to see how this is happening, because see, the rotation is just your g, and x is the painting that you are doing, and your painting is color. Here your x is color two edges with the color black and one edge with the color blue. This is your x, and g is just the rotation which sends this triangle to this triangle. So this and this triangle are in the same orbit. Okay, so somehow you are using this group action, or I can say you can write this entire thing in the term of group actions using the action that we have defined. And in this question, it's just computing the orbits of this group action. When your x is coloring everything with blue, coloring everything with black, coloring two sides with black and blue, and coloring two sides with blue and one with black. So your capital X, the set has four elements, and your G is just D3. Okay. Similarly, here your X has again four elements. One is to color with blue, green, and black, leaving the red alone. And the second you can take maybe coloring with green, black, and red, leaving the blue alone. And similarly two others. And then we are we want distinguishable triangles. So forget about this note vertices. This triangle and this triangle is not distinguishable to a person because they are colored in the same pattern. If we just don't focus on these vertices, the naming is not there because anything is not written. It's just a equilateral triangle. It's not a labeled triangle. I am labeling it just to explain you what's happening. But in general, it's not a labeled triangle. So this triangle is not distinguishable to this triangle. So for us, this and this is same in question number 3. And why they are same? Because they belong to the same orbit if we are defining the action like this. Okay, in both the question, what's the difference is we are just changing our x, the capital X. Okay, and in both the questions they are having the four elements, and each of them is giving us an orbit. So that's why uh, we in both the questions we got answer as 4. Okay, so I hope this seems interesting to you. Your question, see, the answer we have already calculated. Why we I did all this so that you guys can become more familiar with group actions, and uh, you feel it to be more interesting. So I think we can move to the next question. Yes,
Yes, sir.
let's look at question for a moment. It says given three integers a, b, and c. Uh, oh, someone is writing in the chat. So if you have any doubt, please uh, you can unmute yourself and say. Okay. Oh, so if you have a doubt why it's not 8, the problem statement is not clear. Just saying distinguishable does not make it clear to include rotations as the same. So I hope now it should be clear. It should, by distinguishable is just like you can visualize it as two different elements. Forget about this labeling. For a person, this triangle and this triangle is same. who don't know mathematics, for that person this triangle and this triangle is same, right? So it's like that. If you handle this a triangle with this coloring pattern and this coloring pattern to a child, he will say, yeah, both are identical. Okay. So uh, by distinguishable, it just mean that. I hope, Cliff, I have cleared your doubt. Okay, so let's move to the next question. It says, given ABC uh, integers, f of ABC is a map from z cross z to z, defined as x comma y mapped to ax square bxy, uh, x square plus bxy plus cy square. So this element is an element of integer. Sorry, it's this element is an integer because you are just multiplying and taking products of integers. So it's an element of this uh, z. Now let x is the set of all these maps. For each ABC in Z, you have these maps, and X is the set of all these maps. And let GL2Z with a group of matrices with integer entries and having determinant to be plus minus 1. Now consider the right action of GL2Z on X given by F A comma. Okay, so I will explain this action. This action says right action is just like you can say it's a different way of denoting it. Okay, it won't be a problem in defining it. You were writing it as z dot x. Now they are saying it to be x dot g. But you have a definition that f a b c dot a is just f a dash comma b dash c dash, where a dash b dash c dash are such that this matrix is equal to a transpose multiplied with this matrix and a. So let us first understand this section, then we will see what is the requirement of the question. Okay. So say for if you pick one, two, three, or it's better to just use the whatever is asked in the question itself. So this belongs to uh, z cross. All these are integers, right? So I'm just not writing it. What is this f121? So f121 is just a map from z cross z to z, sending any tuple uh, although I don't think that this map has anything to do with the question, but let's write it. So f of a comma b comma c acting on xy is x square plus bxy plus cy. So it just send it to x square plus 2xy plus y square. Okay, and now your uh, matrix you have to choose. So uh, let a is something like, first of all, it's a group with matrices, group of matrices with integer entries and determinant to be plus minus 1. Okay, so you need to find a matrix which has determinant plus minus 1 and all the entries to be integers. So I can take this and this matrix. It belongs to GL2Z. What's the determinant of it? Can anyone tell me?
-1.
Yeah, so minus 1. All entries are integers. Its determinant is minus 1. So it belongs to GL2Z, right? Now, how this action is defined? F of 1 comma 2 comma 1 dot a uh, is used as a general notation. So I won't prefer going with the same notation. So because we are choosing a specific matrix and they are saying for all uh, a, let's just change the notation to B. So f dot B will be some f a dash b dash c dash such that your 2a dash b dash then b dash 2c dash is same as a transpose, which is b transpose, and 2a b b c, and this is transpose. How they are denoting the transpose? How they are using small t. Okay, so we will also go with the small t notation, and it's b. Okay, so we have what is b? B is just 0 1 1 0. A is we all know A is 1, B is 2, and C is 1. So 2A will be 2, B is 2 already, again B, and this 2C is 2. So whatever you get after this multiplication, okay, so after this multiplication you will get a matrix. The first entry of that matrix, let's say it is something R S. It first of all it has to be something of this form, RSST. So that will give you the choice of A dash. So A dash will be your R by 2, B dash is simply S, and C dash is T by 2. I'm not good doing the multiplication, that's up to you. Okay, so I'm just stating here result, and or rather than I just state it like that, that for some RST belongs to Z. Whatever is the outcome of this multiplication, it should be of this form, and then you can compare this with this matrix. So you will get the choices for A dash, B dash, and C dash, and then corresponding to that you have a map f A dash, B dash, C dash, and that map is the uh, is equal to f121 dot p. Okay, so that's how this action is being defined. So we need to first check that this is indeed a right action. Which of the following are not in the orbit of 1 to 1? So I hope you can check that it's a right action. First of all, see, the identity axiom is trivial, I guess, because if you have I in place of B, then what it will do? It will be just I transpose your 2A B C and then I. So you will again get this matrix, or at least identity axiom. I can just write down, and uh, it should be clear. So f of ABC dot I identity, for that this is A dash, B dash, and C dash, such that you have 2A dash, B dash, B dash, and 2C dash equal to identity transpose, then 2A B B 2C, and then again identity. So it's just 2A B B and C, which implies that your tuple A comma B comma C is same as A dash B dash C dash, and which just proves the identity axioms, right? That f of A comma B comma C dot identity is f of A comma B comma C. The other uh, thing is also easy. I think, okay, let me just do it. f a comma b comma c dot two elements, say we pick two matrices b comma c. It has to be some a dash b dash c dash, such that f, the same matrix again, 2 a dash b dash b dash 2 c dash is this matrix bc transpose 2a b b 2c, and then this bx. Now it can be written as c transpose, because bc transpose is just c transpose b transpose, so it's c transpose multiplied to this matrix 2a b b 2c, and the notations are so bad. So okay, so this is a matrix 2a 2b 2c, then this is a bracket, not a matrix, and then you have c outside. So it's just the outcome of b transpose 2a b b 2c b, and then multiply with c transpose and c. So I hope that it's clear. It should be clear to you guys that f of a comma b comma c dot bc is same as f a comma b comma c. First you operate act b on it and then c on it. So that's what we are doing in the definition also, that it's when you are operating with bc you are getting that the same result as you get first operating b and then c. Okay, so this makes this action to be a group action. This implies we have a group action, right?
Yes, sir.
So now we also need to check that whether these elements belongs to the orbit of f123, sorry 121. Which of the following are not in the orbit of 121? So let us first state the definition of orbit of 121, and then it should be very clear. Orbit of f1 comma 2 comma 1. So it will contain all those elements f a comma b comma c, such that uh, a of f121 is f of a comma b comma c for some a in your GL2 set, right? I hope they are using the notation GL2 set. Just let me check. Yeah, GL2 z. Okay, so this is the definition of orbit of uh, f121. But what does this means? This means that you have 2a, b, b, and 2c to be equal to a transpose 2. For this, what is the first coordinate? That is 1. So 2 times 1, that is 2, right? The second coordinate is 2, so it has to be same as it is 2 and 2. And the third coordinate is this one. So again, you have 2, right? I hope it's clear. How I'm writing this?
Yes, sir.
Okay, so it's just coming out from the definition of this. Okay, I don't know what happened. Somehow my keypad is locked. You can see the screen, right? Oh, hello, can anyone hear?
Yes, sir.
Okay, yeah, now it's okay. So if something is equal to this matrix, then their determinant should also be same, right?
Yes, sir.
Okay, just a second. So what is the determinant of the right hand side matrix?
4AC minus B square.
This is supposed to be the left. Okay.
It is left.
uh, Determinant of this matrix.
This is equals to determinant of A transpose into determinant of this matrix, which is 0 into determinant of A. So whole thing is 0.
Yes, good. So determinant of this is 0, so it has to be 0. So whatever ABC is, uh, it must satisfy this condition, that the determinant of the matrix 2A, B, B, 2C has to be 0, right? So from the available choices, you can verify that only the one with let me see. Yes, only 1, -2 and 1. For these values of A, B and C, you will get the determinant 0, and for uh, F123, F -3, 2 -1 and F111, these three won't give you the determinant to be 0. Okay, it's just putting the values of A, B, C and computing the determinant. I hope you can uh, do this of your own. Okay, so
Yes,
for
sir.
F 123, F -3, 2 -1, and what is the third one? Yes, it is 111. So for these three, the determinant won't be 0. So these three won't be there. So if you just need to uh, click or just need to tick an option, you can say, okay, its determinant is non-zero. So that only one option has to be correct. That's the fourth one. Uh, this condition is not satisfied. You can check it. And for the last one, F1 -2 and 1. What we have, uh, 2A is 2.1, that is 2, so it's just 2 times 1. B is -2, again here B is -2 and C is also 1, so it is 2. So it's the determinant of this matrix 2, minus 2, minus 2, and 2. Its determinant is 0, right? So
Yes.
it gives you, it's a candidate of uh, ABC. But we are fortunate enough that all three options have been cancelled out, so the fourth option has to be correct. But being students of mathematics, we should give proper justification that why this matrix is in the orbit of uh, uh, 1 to 1 to 1. Okay, so you can see for for this choice of A, 1 1 0, we have that's not it. 2 minus 2 minus 2 and 2 to be equal to A transpose the matrix which we are getting from 1 to 1. Okay, we need to satisfy this condition, right? 2a b b 2c is A transpose 2 2 2 2 and A. So for this choice of ABC, we have 2a b and 2c as this, and so it has to be some A transpose times this matrix 2 2 2 2 and then multiplied with this A. So for this choice of A, you can verify that this happens. And the interesting thing is, which I leave to you guys, this choice of A is not at all unique. You can find many other choices for A. So try to find some different choice of A for which this happens. Okay. But just keep one thing in mind, your element must be an element of GL to Z. You can see here that all elements are are integers and the determinant is 0 minus minus of 1. That is determinant is 1. So we are having determinant to be 1. So it's an element of GL to Z. So what else you can find which gives you these conditions being satisfied. So this implies that the fourth option is correct, right? So only the fourth one is in the orbit of f121 and others are not. Okay, I hope it's clear to everyone.
Yes, sir.
Yeah. Okay, so for fifth question, it's just a counting question. I will just give you some hints, or whatever data you require, and then I expect that you guys should be able to do it, because counting will unnecessarily take the time and it's not fruitful. So D4 uh, is just the set of this form Ri Sj, where such that you have R squared, R4 is equal to S square is equal to identity, and Rs is same as S R inverse, and of course this I is between 1 to 4 and J is between 1 to 2. So just an group with this set R, 1 R, R square, R cube. Then you have mm, S,
S
yes,
S square S
S
R
square is identity,
S R.
SR, but we are writing it
Yes.
as RIJ. So I will
R
prefer you can,
S
yes,
R S R S R square S R cube S.
yes, R square S and R cube S. Okay, so these 8 elements we have. Now you will need the data for conjugation, conjugacy classes, because it's just a conjugation action. So you need to compute the orbits under this action. So you pick an element, say of D4, say 1 comma 1, then where it can be mapped to, and a element of say 1 comma R, then where it can be mapped using this action. So it's like a double conjugation. Okay, so for I'm giving you the data for conjugacy classes, and then it's just computing using the definition of it. Okay, so conjugacy classes of D4. So first of all, identity has to be a separate class. R square is also an element of center, so it has to be a separate class. Then for all others, they are not the central elements, so at least two elements should be there. And here we are just having two elements for each in each non-central conjugacy class. So R cube, we have S, R square S, and the last one is S, RS, and R cube S. All eight elements covered. So now it's your task to use this information to get the correct answer. Okay, and which is 28.
Sir, excuse me, sir.
Yes,
Sir, the group action defined in this question is not visible. Can you please write it again?
it's G dot x1 comma x2, G x1 G inverse, comma G x2 G inverse. Anyway, you will get these notes. So once you get the note, you can try to solve these questions again. Okay.
Okay, sir. Thank you.
I will upload the lecture by on that um, YouTube channel by tonight. Through NPTEL, you will get the link, I think, in 2 3 days. So it's up to you that when you want to solve these questions. Okay, so let's move on to the next question. Question number 6. So consider the natural action of GL3 F2 on F2 3. What is the size of this stabilizer of this uh, E1? Okay. Uh, so this is again an interesting question. It will take some time, but let's do it because it will clarify your doubts regarding the group action. So see what is the natural action. First of all, you we have to see that because the action is not explicitly defined. They are just saying that this group GL3 F2 is acting on F2 3. So if anyone is not aware of this notation, so GL3 F2 is the group of
Two cross two matrices with
all 3 cross 3
three cross
matrices.
three matrices with
Mhm.
two elements, field of two elements.
Yes, with elements from F2. Okay, so this group is acting on the set of this 3 cross 1 vector with entries in F2. So what is the natural action that we can get from here? That an element A dot X is just mapped to A times. It's just a matrix multiplication because it's a 3 cross 3 matrix and you have a 3 cross 1 vector, so the matrix multiplication is well defined. Okay, so it's just a matrix multiplication. So it's the natural map. Just multiply the matrix uh, with the vector. Matrix multiplication. Okay, yeah. So we need to find the stabilizer of this even, uh, size of stabilizer of even. So we will explicitly calculate what is this stabilizer. So stabilizer of even is just all elements in GL3 F2 such that G dot even is even. Okay, and what does this mean? So I think here we are using matrices, so it's better to use the notation A here. G is also fine, but we have used the notation A above, so let's go with the same notation. So we need all these matrices which fixes this even. So we pick an arbitrary element of this HI. Okay, let this belongs to GL3F2 such that it satisfies this condition that A dot E, so this is our A, and this is our E. It again giving you this 1 0 0. So can you tell me what condition we can get from here? What is this
After
multiplication? Huh?
after multiplying, we get A equals to 1, D equal to 0, or G equals to 0.
Yes. So it's A D G, right? Which has to be 0, which has to be same as 1 0 0. So this implies A is 1, D is 0, G is 0, right? So if something belongs to the stabilizer of it, then uh, it has to be of this form: 1 B C 0 E F G H I.
G is also 0.
Oh, yes, yes. Thank you. I think I made a small mistake in defining the in, in the definition. So group of all invertible matrices. Group of 3 cross 3 matrices does not make sense because we are using the operation as multiplication. So group of all
Yes.
invertible matrices, invertible 3 cross 3 matrices. Okay. So what is the determinant of it? This matrix.
E into I minus HF.
Or I can simply write that it has the same has same determinant as this sum matrix E F H I.
Yes, sir.
Yes. So can we say this, that uh, let's say this matrix we denote it with A. let A is equal to this, can we say that A belongs to GL3 F2 if and only if, first of all, B and C has to be elements of F2, right? And E, F, H, I belongs to GL2 F2 because it has a non-zero determinant if and only if this A has a non-zero determinant. Yeah. Yes. Oh, sorry. Uh, what I'm writing. Uh, this belongs to stabilizer of even because stabilizer of even is giving us all this condition. Na? We assume that uh, we has to assume that this, yes, it is okay such that this belongs to this. Okay, okay. So this is okay that here it's okay that it belongs to GL3 F2 such that this condition is satisfied, and once this condition is satisfied, we are assuming that this element is an element of stabilizer of even. So A is belonging to stabilizer of even will give us this condition that A has to be of this form, and this matrix has the same determinant as this matrix. So A belongs to stabilizer of even if and only if this BC belongs to F2 and this matrix has non-zero determinant. You all agree to this?
So can you please repeat this?
Ha. Okay. So we first write down the definition of even. It's just an element of GL3 F2 which fixes even. Okay. And the action is just the multiplication action. So uh, let A is this matrix. It's an element of GL3 F2. So we need to satisfy this condition if we want A to be inside this stabilizer of even. So we are assuming A is inside GL3 F2 such that this A fixes this 100. So if this fixes 100, we get that A is 1, D is 0, G is 0. And in addition to that, so what kind of A we can have now? We can have matrix with 100, B, C, E, F, H, I, right? And this matrix has the same determinant as this sum matrix of it because this matrix has the determinant EI minus HF, and this matrix also has the same determinant EI minus HF. So this matrix belongs to GL3 F2 if and only if this matrix belongs to GL2 F2. You all agree? Because this matrix has non-zero determinant if and only if this matrix has non-zero determinant. Clear?
Yes, sir.
Okay, so any matrix belongs to stabilizer of even if it satisfies these two conditions. First of all, it must fix uh, this 100, and that implies that this matrix has to be of this form, and then this matrix belongs to GL3 F2 if and only if this submatrix belongs to GL2 F2. So this belongs to stabilizer of even if and only if B and C are arbitrary. You can choose them in any manner you want, but they have has to be elements of F2. Okay, and EFHI belongs to GL2 F2. Okay, so uh, I'm again taking an extended time, but I hope you guys are getting something. Uh, so order of stabilizer of even is order of F2 because B can be chosen arbitrary from F2 times the order of F2. This is choices of
B
B.
and C.
Yeah, this is choices of C, and then the order of GL2 F2, right? And this is for choices of this matrix EF Let's check. Clear? So it's just 2 into 2. It has order 6. We, if we get, if you are guys are interested, then I can also tell you that how we get the how we can prove the order of GL. We can compute the order of GL and FP in general and SL and FP in general. But you have to stay with me for some more time, and in the next question we will do it. Okay. So for the moment you can just assume that it's given that the order of GL to F2 is 6. We will compute it explicitly just after a while. So it has order 24. Okay. Now I think we can move to the next question. This question is again interesting. Uh, you are given an undirected simple graph with vertices 1 to 6. This is your graph. Okay. Mm, let G be the automorphism of this graph. Okay, for this graph you are having automorphism group. So already, although I have explained again and again what is an automorphism group of a graph, but let me just write it again. Some sigma belongs to here Sn. We have n is 6, so sigma belongs to Sn S6 such that Eij belongs to this age set of edges if and only if your E sigma of I sigma of j belongs to the set of edges. Okay, so all such elements of this permutation group which preserve this set of edges, that is your automorphism group. We have already seen this a number of times. uh, So now it's saying the order of the silo 2 subgroup of G is 216 or silo 3 subgroup is 39. So we will explicitly compute what this automorphism group is, and if we have the explicit computation of this order group, then we will be able to answer this question. Okay, so uh, just pay some attention because for the first time we are going to compute an automorphism group of the graph in our tutorial. So it might be a bit tricky. So see, say we fix an element 1. So let uh, okay, let sigma belongs to S6 be such that sigma of 1 is 1. So we fix up index 1. So sigma is such that it is fixing 1. So what this implies, where your 2 can be mapped to. See, 1 is mapping to 1 and 1 and 2 is an edge. So sigma 1 and sigma 2 has to be an edge after if the sigma is an automorphism. So what choice you have for 2? Anyone? 1 is mapped to 1. So where this 2 should be
Sigma
mapped so
2,
that, huh?
2,
Yeah. So sigma 2 is has to be this 2 because 1 and 2 has to is already an edge. And sigma 3 has 4 choices. It can be 3, it can be 4, it can be 5, or it can be 6. Okay. And once sigma 3 is fixed, then your sigma 4 is also fixed because let's say here if it is 3, what does this implies? It will imply that sigma 4 has to be
4,
4. Okay. And here if sigma 3 is 3, sigma 4 has to be, sorry, sigma 3 is 4, then sigma 4 has to be,
3.
yeah, 3. And similarly here you can see that sigma, if sigma is 3 is mapped to 5, then 4 has to be mapped to 6, and if 6 is mapped 3 is mapped to 6, and 4 has to be mapped to 5. Okay, so these four choices you have. So for this choice of uh, sigma, you have four choices, and you have all got the image uh, for uh, uh, images of 2, 3, and 4. Now we have to see what can be the images of 4, 5, and 6 also, right? So if sigma 3 and sigma 4 of this are of this kind, then again uh, this can lead to two options. First is sigma 5 is 5 and sigma 5 is 6, right? Because till now we have the computation for sigma 1, 2, 3, and 4. Okay, so sigma 5 can be fixed, or it can be mapped to 6. And if it is mapped to 6 5, that will imply that sigma 6 is 5 6. And if it is mapped to 5 sorry, if it is mapped to 5, then it will imply that sigma 6 is 6. And if it is 6, then it will imply that sigma 6 is 5. Similarly, two choices in this case, and two choices in this case, and two choices in this case. I hope it's clear, Shalini.
Yes, sir. Yes, sir.
Okay, so uh, total 8 choices you have.
Yes.
When sigma 1 is 1. Similar computation if you do with other cases, you will realize that similarly when sigma 2 is 2, you have 8 more choices. And definitely these choices are different from the previous one, because the image of, oh, silly thing I'm doing here, it's sigma of 1 is 1. 8 different choices. And for sigma 1 to 3 and so on to sigma 6, for each you have 8 choices, 8 different choices. Okay, so the total number is, yes, Shalini, can you tell me total number of choices? 8.
8 into 6.
Yeah, 8 into 6, that is 48. 48 is already an option, which is the correct one. Oh, sorry, this is just the order of the group. Okay, uh,
Silo.
now silo 2 subgroup has the order. Out of this has order 48, so which is, can say which is equal to 2 raised to 4 not 3. Okay, so from here it uh, order of silo 2 subgroup is
16.
16, and order of silo 3 subgroup
3.
3. Yes, order of silo 2 subgroup is 16, and order of silo 3 subgroup is 3. Okay, so today we will discuss one more question, and rest of the question will be discussed in tomorrow's uh, discussion session. Okay, tomorrow's you have one more discussion session, right, with some other uh, instructor, so he will discuss rest of the questions. So this is the last question for us. It says, for a prime P, SLN P denote the subgroup of GLN which consists of matrices with determinant 1 modulo phi P. Which of these statements are correct? The order of silo P subgroup. So we just need to compute the order of silo P subgroups of GL and FP, and the order of silo P subgroups of SL and FP. So as I promised you that at the end we will be computing the order of GL and FP and the order of SL and FP. And once we have these orders, from that order we can immediately say what are the orders of their silo P subgroups. Okay, so let's do the computation for the order of GL and FP. Okay, submission, order of GL and FP. So it's the group of all invertible matrices with entries in the field FP. Okay. Uh, so see, if A belongs to GLN FP, then say this is your matrix A. Okay. If this belongs to, or just if this belongs to GLN FP, mm, we denote, say this is your row 1 and this is row 2, so on to it should have n rows, right? Now row 1 can be chosen arbitrarily from the elements of FP, except you can't choose the 0 row. Okay,
Yes, sir.
except 0 row, row 1 can be chosen arbitrarily. Can we choose? um, okay, so how many choices you have? Each element is chosen from FP. You have n elements in row 1, and so p raised to n, and then minus for 0 row, right? So you have Pn minus 1 choices, right? Now for row 2, so row 1, row 2 should not be a linear multiple of row 1, because if it happens, then these two rows will not be linearly independent, and that will make them non-invertible. Okay, in an invertible matrices, each you have rank n, so each row is linearly independent. So for row 2 it should not be
Linear
li-
combination.
linear combination of row 1. So you have everything is acceptable except linear multiplication, and for this alpha you have p many choices. Okay, so this alpha has p choices, so you just sub- subtract these p choices from it. So pn minus p choices you can have. So there are pn minus p choices for row 2. Now for row 3, I need to use a different color again. So row 3 should not be a linear combination of row 1, right? It is beta of Okay, so everything is acceptable except the linear combination of these two. So for alpha you have p choices, and for beta you have p choices. So subtract these p square choices, and uh, anything else you can pick. So going through the same pattern, uh, you can say that row n cannot be uh, a linear combination of row 1, row 2, so on to row n. Okay, so oh, row n minus 1. So the acceptable choices are Pn, total number of choices, minus these choices. So which is P raised to n minus 1, because for each alpha you will have P many choices. That's why you have these many choices, right? So now the order of this implies the order of GLN FP is, for first row you have how many choices? P n minus 1. For second row you have Pn minus p choices. For third you have Pn minus p square choices, and so on to Pn minus p n minus 1 choices. Okay, so this is the order of GLN FP for any n and for any prime p. Okay, now the question says the order of silo p subgroup of GLN FP is. So we need to separate out powers of p. So from first you won't get any power of p, it's just Pn minus p, Pn minus 1, and here you will get p. You can take out this p to be common from here, and uh, from here you can take out p, from here you can take out p square, so on to from the last one you can take out p n minus 1. So it will be p dot p dot p, so on to p n minus 1 times Pn minus 1, because first multiplication, this is independent of p, so we haven't taken out anything from here. We have taken out this p, so, and here we have taken out p square. Okay, uh, so on to we have p minus 1. Okay, now it's up to you to check that, of, although it's obvious that this all these entries, all these products are co-prime with p. Okay, why it is obvious? See, if this is divisible by p, then you can say that already p raised to n is divisible by p. What does this mean? Their difference is also divisible by p, which implies this, that is minus of 1 is also divisible by p, which is not true. Similarly here, this term is divisible by p. So if the entire term is divisible by p, then this minus 1 is divisible by p. Similarly, here also p is divisible by the prime p. So 1 minus 1 cannot be divisible by prime p. And thus the powers of p in this product is only this much. This much is, this part is co-prime with the prime p. Okay, so it's co-prime with p. So order of p silo subgroup is just p plus 1 plus 2 plus so on to n minus 1, right? Only this part, which is
Yes, sir.
okay. Yes, Shalini. So it's n minus 1 times n upon 2. Okay. Just the sum of natural number n, n plus 1 by 2. So here our n is n minus 1,
And
n by
minus.
2.
Yes, sir.
Okay. Mm, so this option is correct. The first one. I have put the bracket in a very wrong manner. It should be here. Otherwise, it would be n minus 1, that is 0. Yeah. So now, with the help of this, can we compute the order of the uh, SL and P? So that's even simpler to this. Okay. So order of SL and P. So see, if A belongs to SL and FP, uh, such that your A is a matrix of this kind. Let's say A 1 1, so on to A 1 n, and A n 1 to A n n. Okay, then, or I should say A belongs to this, so that A is this, if and only if this matrix alpha times A11 dot A1n, so on to A n1. I am not multiplying alpha to anywhere else, just in the first row. Okay, so what is the determinant of this matrix? Mm, this matrix is an element of SL and FP. So it has
It
determinant
should
1,
be 1.
and this alpha times the first row of this matrix, and all other rows are same. So if this belongs to SL and P, if and only if this element has determinant equal to alpha, right? Because it has determinant same as alpha times determinant of A, right? And determinant of A is, so determinant of A is 1 if and only if alpha times determinant of A is the determinant of this matrix. So definitely we have to fix first alpha is some non-zero number. Okay, fp minus the set 0, some non-zero element of fp. Because if this element, if this has determinant alpha, uh, then determinant of A will be a determinant of this matrix divided by alpha, which is 1, and this matrix as determinant 1 will imply that this matrix has determinant alpha. So in you have a bijection, we have a bijection between SLN FP and the set say K alpha, where it is a set with determinant equal to A belongs to GLNFP such that determinant of A is equal to alpha. Okay, where alpha is a non-zero number. I should write it here also, where alpha is any anything which is non-zero. Do you agree, Shalini?
Yes,
What
sir.
what is a bijection? Just map a matrix A to a matrix of this form such that the first row is alpha times the row of this matrix A and all other rows are fixed. So if this matrix has determinant 1, then this matrix will have determinant alpha, and it's a bijection because from here to here you can define the inverse map to be just multiplication by alpha inverse in the first row. Alpha is non-zero. Okay, so we have bijection between SLN FP and the set K alpha, and the this set GLN FP is the union of, oh sorry, is the union of all these set K alphas. Here alpha can be 1 also. No, I'm not saying that it's not 1. It's just non-zero number. So it's a set having a determinant to be alpha. Okay, and what are the possible choices for the determinant of GLN FP? It should be viewed modulo P, right? First of all, and it should be non-zero. So the possibilities are 1, 2, 3, so on to P minus 1. So uh, GLN FP is just a union of K alpha, where alpha belonging to FP minus 0. Okay, and we have seen that elements have all these sets have the same cardinality. Why? Because they are all uh, uh, in bijection with the set SLN FP. So SLN FP is nothing but your K1. So all these set has the bijection with this set SLNFP. Okay, so and their intersection is zero. Their intersection is empty, right? A matrix cannot have a determinant alpha and beta if alpha and beta are different. Okay, so this will implies that order of GLN FP is just the sum of uh, order of these K alphas, where alpha belongs to FP minus 0, because this is a disjoint union, or not. Disjoint union is not a correct word because it has a different meaning in topology. So I will just say K alpha intersection with K beta is empty if alpha not equal to beta. Okay, so and all these are in bijection with K1. So for each non-zero integer, non-zero element of FP, you have to take the sum of it. How many non-zero entries are there in FP? Just P minus 1, right? So you have it to be P minus 1 times the order of K1. And what is our K1? K1 is nothing but SLN FP, right? So order is also there. Order is also there. Okay. So this will implies that the order of SLN FP is order of GLN FP divided by P minus 1. And what is the order of this? You already know the order of GLN FP, right? So If we divide it with p minus 1, the last factor will be removed, and you have the same uh, uh, power of p, because this was anyway co-prime with p. In the this first products were playing role in this in the order of this p shallow subgroup. So the p shallow subgroup of GLN FP and the p shallow subgroup of GLN FP is it clear?
Yes, sir.
Shalini, con- do you want me to repeat it, or it makes sense?
Clear, sir. Clear.
Okay, okay. So that's it. Its order is uh, we have already computed its order. So this implies the p silo subgroup of SLN FP and p silo subgroup of GLN FP has same order. Thus, this question is solved. Okay, so uh, the first two options are correct, and the last two are incorrect. Okay, the next seventh question will be solved by the other TA. I hope everything is clear. If you have anything to ask, then you can ask me. Otherwise, we will stop the meeting here.